We are now going to go over to a second category of two-dimensional experiments, namely two-dimensional correlation experiments. These have been by far the most useful experiments for studying a variety of systems, large systems, small systems, etc., and has been extremely useful in characterizing molecules, understanding the fine structures in the molecules, understanding the connectivities of the individual carbons in molecules, and so on and so forth. And typically it started with homonuclear proton correlation experiments, but today we also have various kinds of correlation experiments which deal with proton or carbon 13 and proton with nitrogen 15 and so on and so forth. So first we will look at the proton-proton correlation experiments, and this because in the initial years it was all homonuclear proton experiments only which were designed, and they were used for variety of purposes. So this experiment is called as the COSY, correlated spectroscopy. So the abbreviation is COSY, and it is very commonly used for all organic chemistry and biochemistry and biological chemistry and whatnot. So this experiment consists of a simple pulse sequence. It is an experiment with the 2 pulses. You start with a 90-degree pulse, it can be x or y or whatever, but conventionally we are simply sticking to x all the time, and then you followed by a T1 evolution period, then you have another 90-degree x pulse, and followed by the detection during the period T2. So in this period of course you may have this what we call as the preparation. This includes the 90x pulse in the preparation, then you have the evolution. This pulse 90x pulse here itself acts as the mixing pulse in the generalized context of 2D spectroscopy, and this is a mixing pulse, and then you have the detection here of the signal during the T2 period. Now we will see that this kind of an experiment produces a spectrum of this time. This is a schematic experiment. So if I call this as F2 axis, which is where we actually detect the signal, and this is the indirect detection axis, we call it as F1, and that comes as a result of Fourier transformation along the T1 dimension. Okay. And now let us see what is the information here. If you generate peaks like this, so I will have a so called diagonal here. The diagonal will have the same frequency along the F2 and the F1 axis. So therefore all these peaks which are here, they have the same frequencies whether it is along the F1 or the F2 axis. Now then it displays correlations here. It displays, these are called cross peaks, and the cross peak displays a correlation between this particular spin and this particular spin. When if I were to talk all this as protons, it is this proton and this proton, there is a correlation between these two. Where does this correlation arise from? This arises from the coupling, from the J coupling. In this experiment the correlations arise as a result of J coupling. These two protons are coupled to each other, and therefore it produces a cross peak here, and this is called as the cross peak or the off diagonal peak. And now you notice that this peak is also attached to another proton, and that is this proton is also coupled to this proton. Therefore we generate a cross peak here as well between these two protons. Okay. So therefore this forms a network. So you have a network of spins here. These 3 protons are coupled to each other. This is coupled to this and this is coupled to this, and we produce peaks on both sides. So this will be a symmetrical spectrum here, and no matter which side of the diagonal you use, the information is the same. Now if there is a proton in your molecule which is not coupled to anything, it will produce what is called as a singlet, and it will not have any correlations along any of the axes there. Therefore it will be easy to identify which of your protons are singlets which are not coupled, and which of your protons are coupled, and what sort of coupling pattern spin systems exist in your molecule. So this is an extremely useful information for characterizing your molecular structures. Okay, let us try and understand this using our the standard method of product operator calculation. So this is the cosi of 2 spins. Once again we choose 2 spins k and l. So at the time point 1, so I have written here time points 1, 2, 3 and 4, we will explicitly calculate the density operator at these individual time points, so that we know what is the information content here and how the information is flowing through the pulse sequence. Okay. So at time point 1, so I have the equilibrium magnetization, so the density operator is IKZ plus ILZ considering the 2 spins. Now individually we can calculate the evolutions of this through the pulse sequence, but let us, for demonstration we will consider only the K spin, and whatever results we generate, similar calculations can be done for the L spin as well, and therefore we do not want to repeat that for the 2 things. So we consider the calculation for the K spin only in the further discussion. Now so if I apply 90x pulse to the K magnetization, I generate minus IKY as before. Now this evolves under the Zeeman Hamiltonian, which is omega k IKZ for a period t1, yielding the density operator rho 3 at time point 3 in the pulse sequence. So now considering the chemical shift evolution, the IKY terms evolves in this manner, the minus sign is kept out here. So I have here IKY cosine omega k t1 minus IKX sine omega k t1. Now we have to consider this further for evolution under the coupling. Next, considering evolution under the J coupling Hamiltonian, which is 2 pi jkl ikz ilz. So the density operator will be, let us say, rho 3 prime. So the rho 3 prime will be given by, keep this minus sign as before, and now we individual terms, these operators we have to evolve under the coupling. Okay. So IKY evolution gives you this IKY cosine pi jkl t1 minus 2 IKX ILZ sin pi jkl t1, and you have this cosine omega k t1 from here. And this term gives you minus IKX cosine pi jkl t1 plus 2 IKY ILZ sin pi jkl t1, and the sin omega k t1 comes from here. Now so this is the density operator at the end of the t1 period. Now what we are doing at the end of the t1 period? We are applying a 90-degree pulse again. So here we notice that after we apply the 90-degree pulse, these terms will get transformed into the particular manner. We get here at rho 4, the first bracket gives me this IKZ cosine pi jkl t1, because I apply 90x pulse, this was ky here and ky goes to kz, and here it was kx lz, lz goes to ly, therefore I get here 2 ikx ily sin pi jkl t1 and cosine omega k t1. The second term remains like this, the kx is not affected, so it remains as kx cosine pi jkl t1, but here you see there is a change. So I get here minus 2 ikz ily sin pi jkl t1 sin omega k t1. Let us look at these individual terms. So you see this one is Z magnetization of the K spin, and now this is a mixture of the double quantum and 0 quantum coherences, okay, and this is the X magnetization of the K spin. Now this one here is the L magnetization, this is the Y magnetization of the L spin, which is antiphase with respect to K. Therefore you see the 90x pulse, the second 90-degree X pulse has caused a coherence transfer from the K spin to the L spin. So from the K magnetization we have generated L magnetization here, so this represents a coherence transfer. Both these are single quantum terms, although this is antiphase, this is in phase, whereas this one is Z magnetization and this is multiple quantum transitions here. You notice that these operators do not lead to observable magnetization during the T2 period, because the next what we are going to have is evolution during the T2 period. Whatever is observable there we are going to retain, and what is not observable we will ignore, because it is not going to lead to us any signal. Therefore these two terms here we can ignore, because though these ones do not lead to observable magnetization and these ones actually lead to observable magnetization, both these are observable terms. Now the first term, which represents X magnetization of the K spin, evolves during the T2 period with frequencies characteristic of K spin, right. So, during the T2 period this evolves with the frequency omega k. In the T1 also we have omega k, in T2 also it will be omega k. Therefore, this will produce the so called diagonal peak which I mentioned to you earlier, F1 is equal to F2 is equal to omega k in the final 2D spectrum. The second term which represents Y micronization of L spin evolves under the T2 during the T2 period with frequencies characteristic of L spin. Therefore, this will have T2 during the T2 period, this will have frequencies of L spin, but T1 it had frequency of K spin. So, therefore, this will be F1 is equal to omega k and F2 is equal to omega L. Therefore, this produces what is called as the cross peak in the final 2D spectrum. Both these peaks will have fine structures which contain the coupling information, and this we can calculate. We can see that immediately from here that the JKL term is appearing here, and therefore, we will have coupling information in these individual peaks. Let us first consider the diagonal peak term. The diagonal peak is arising from IKX, the first term in this observable part. So, a chemical shift evolution leads to the density operator rho 5d. This is during the T2 period. So, I call this as rho 5d, and this is IKX cosine omega kt2 plus IKY sin omega kt2, and the entire modulation of the T1 evolution I simply write it as FD T1, and FD T1 is cosine pi jkl T1 sin omega k T1. So, you recall back, and that is just this cosine pi jkl T1 and sin omega k T1. So, I call this as FD T1. Okay. And now we consider evolution of these terms under the coupling. Evolution under coupling generates the density operator rho 5d prime given by this formula here. Rho 5d prime is now coming from the evolutions of the individual terms here. The first term gives me here IKX cosine pi jkl T2 plus 2 IKY ILZ sin pi jkl T2, and cosine omega k T2 remains from here. And the second one gives me IKY cosine pi jkl T2 minus 2 IKX ILZ sin pi jkl T2, and this sin omega k T2 is from here, and then all of it is multiplied by FD T1. Now, among these depends upon what signal we are going to measure, and we will have to see what are the components which we have to retain. Let us assume that we detect Y micronization. We will have to take the trace of the density operator with IKY. So, when we do that, we will only have this one here. This will represent our signal cosine pi jkl T2 into sin omega k T2 FD T1. Now, put back this FD T1, you have here cosine pi jkl T2 sin omega k T2 multiplied by cosine pi jkl T1 sin omega k T1. Note it is the pattern of these evolutions of the terms in the T2 and the T1 are the same. Here is again a sine cosine multiplication, and again here it is sine cosine multiplication. So, if you want to expand this further, so this will give me, so this is the same thing which is written here, 1 by 4 sine omega k plus pi jkl T2, it will generate 2 terms each, right. So, this will generate 2 terms each plus sine omega k minus pi jkl T2, this is from the T2 from this one here, and multiply the whole thing by this sine omega k plus pi jkl T1 and sine omega k minus pi jkl T1. So, what does this tell you? That already it indicates you there are going to be 2 frequencies along omega 2, that is omega k plus pi jkl, or if you want to take out the 2 in terms of the hertz, if you want to write frequencies, then it will be nu k plus j by 2, and this will be nu k minus jkl by 2, because if you take away the 2 pi term here, so this will be nu k minus jkl by 2, nu k plus jkl by 2. Similarly, here along the F1 dimension also I will have 2 terms, the nu k plus jkl by 2 and nu k minus jkl by 2. So, therefore, this entire diagonal peak will have 4 components, 2 into 2, therefore, this will produce 4 components. and where this is the signal that we detect, where do these ones appear. Now I write in terms of the frequencies, removing the pi part. So I will write in terms of the frequencies. 4 peaks with a dispersive line shape. Why do I say dispersive line shape? Because these all have sign dependence, and we have seen earlier that if there is a time domain signal which is sign dependent, it will produce me dispersive signals. So we will have a frequency peak at nu k plus jkl by 2, nu k plus jkl by 2 along the f1 f2 dimension. Then I will have here nu k plus jkl by 2 and nu k minus jkl by 2. This is along the f1, this is along the f2, and this is again nu k minus jkl by 2 and nu k plus jkl by 2, and nu k minus jkl by 2 and nu k minus jkl by 2. So we will have 4 peaks. These are centered around the nu k frequency. Nu k is my frequency of the k spin. So, and all of these are positive, because you see the previous thing, they all have positive components here. These are plus, 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 all of them are plus, this is plus, this is plus, this is plus. So, all are plus. Therefore, I will have all positive peaks and they all have dispersive line shapes. So, how does the spectrum look like? So, you see this is way the spectrum will look like. I have drawn the diagonal here, so which is running through. So, the similar calculation for the L spin will produce me these 4 peaks. There are 4 peaks here. For the K spin I have shown you the calculation for the K spin. So, all of these are dispersive line shapes and they all have the same sign, and it will produce me a peak of this type. And likewise, if you did for the L spin, you will produce a spectrum of this type. And now this spectrum has been taken from one of the books, NMR Techniques in Organic Chemistry, and particular things have been dropped, and this will come in the next class when we actually discuss the cross peaks as well here, and those peaks are also present here at this point. Those will be the cross peaks. Okay. So, I think we have discussed the diagonal peak here, and in the next class we will look at the cross peaks, how they appear. Okay. So, you can look at these things once more at where these peaks appear, and we have the peaks appearing at nu k plus jkl by 2, nu k plus jkl by 2, nu k plus jkl by 2, nu k minus jkl by 2, nu k minus jkl by 2, nu k plus jkl by 2, and here is nu k minus jkl by 2 and nu k minus jkl by 2. So, therefore, this produces a spectrum which is like this, and we will see later that this sort of a dispersive line shape is not a very desirable thing, and obviously one has to do something different there to get better line shapes in this point. Otherwise, this will mask the signals which are close to the diagonal, and that has been one of the problems of the normal Cozy experiment and developments which have happened to remove those. And we will see of course in the next class how the peaks appear in the correlations, which is the cross peak, and we have considered one part of the density operator. Now we will have to consider the second part of the density operator at time rho 4, and which will then produce us the signals which produce the cross peak. So, we will stop here and continue with the cross peak calculation in the next class.